Okay, how do we measure the change in internal energy? So systems and surroundings exchange energy by heat and pressure volume work. So heat is mc delta T, and work is negative P delta V. So if we can calculate both of these and add them together, we could find out how much change in energy is. So the change in internal energy, delta E, is a measure of all the energy exchanged, both heat and work. So we calculate, we measure Q and W. Now, if there's no change in volume, then W equals 0, right? Because work is negative P delta V. If delta V is 0, then there's no work done. So then that makes things much more simple, right? Now, delta E, the change in internal energy for the reaction, is equal to the heat. So we call that Q sub V, heat at constant volume. So this is called constant volume calorimetry, where we're measuring energy, calories, with a constant volume. It isn't practical to look at or try to measure the temperatures of the individual substances. So, you think about putting that block of copper metal into the water. How do you measure the temperature of the metal as it changes? Do you embed a thermometer in the center of it? What do? That's difficult. And if you're looking at a chemical reaction, it's just pretty much impossible. So instead of measuring the temperature change for the system, for the chemical reaction, we measure the temperature change for the surroundings. And we know that the temperature change of the surroundings, or the energy change of the surroundings, is equal and opposite to the energy change for the system. So Q for the system equals negative Q for the surroundings. The heat lost by the system is gained by the surroundings, vice versa. And so negative Q for the surroundings we call Q cal, the energy absorbed by the calorimeter. The calorimeter is a device for measuring energy. A bomb calorimeter kind of looks like a bomb. It doesn't explode or anything, but it looks like a bomb. So bomb calorimeter is used. It's insulated so that energy cannot be lost to further surroundings. We can minimize our surroundings to just the calorimeter instead of considering the entire universe, which is a bit difficult. So calorimetry is a technique where we measure the heat of a reaction by measuring the change in temperature of the surroundings. And this, we're going to do some calorimetry in lab on Thursday. So by observing the temperature change in the surroundings, we can figure out the amount of heat that was released or absorbed by the system. So here's a picture of a bomb calorimeter. And in the bomb here inside, we've got the sample. And these are often used for combustion reactions. So we've got our sample here. It could be a peanut. It could be sugar. This is how they figure out the calorie content of many foods. So you put it in there, and there's oxygen in this container, and then it's sealed. It's an airtight seal, so the volume of that container can't change. Will the pressure change? Most likely it will, but it's not going to explode or anything. And then we have, I know that would be fun, ignition wires come in here so that we can start the combustion, kind of like lighting a match. So this is tightly sealed, and then it is in a larger container that has water. We've got a stirring mechanism here so we can keep the water moving around. We've got a thermometer. Oh, I hate when that happens. We've got a thermometer here so we can measure the temperature of the water. So Q for the calorimeter equals the specific heat capacity of the calorimeter times its change in temperature. And that's going to be opposite to the heat of the reaction. So heat of reaction is equal to heat at constant volume, which is the change in energy of the reaction. There's a lot of simple but sometimes confusing little math derivation type things in here. So for the calorimeter, this is the heat capacity as opposed to the specific heat capacity. And the reason we do that for a calorimeter is because the mass of the calorimeter isn't changing. And so then we just have the one number to deal with. And that number is determined experimentally, and you make a note of it, and then you can use it in calculations. So let's do a problem. When 1.550 grams of liquid hexane undergoes combustion in a bomb calorimeter, the temperature rises from 25.87 degrees to 28.13 degrees Celsius. Find delta E reaction for the reaction in kilojoules per mole of hexane. The heat capacity of the bomb calorimeter, determined in a separate experiment, is 5.73 kilojoules per degree Celsius. Now that sounds a little bit overwhelming, right? Like, it's going to be okay. So let's write some stuff down here. So we've got a mass, right? So we have 1.550 grams of hexane, C6H14. I'm going to call that M sub H, H for hexane, because I'm not going to be changing colors here. So it's in the bomb calorimeter. The temperature rises from 25.87 to 38.13. So we could figure out the change in temperature for the calorimeter. It's the final temperature of the calorimeter minus the initial. So the final is 38.13. The initial is 25.87. We don't know anything about the temperature change for the hexane. All we can measure is outside the little bomb. So we got 38.13 minus 25.87, 12.26 degrees Celsius. That's the temperature change. And then it's saying, find this, and here are the units, and then the heat capacity of the calorimeter. So that's C for the calorimeter. And that is 5.73 kilojoules per degree Celsius. So what we know is that the heat of the reaction has to be equal but opposite in sign to the heat of the calorimeter. The calorimeter, the outside is insulated and there's not any transfer of energy. So whatever heat is given off by burning this hexane goes into the water and heats it up. So what does Q for the calorimeter equal? It would be MC delta T, but for the calorimeter, we've combined M and C together. So this is negative M, not M, C calorimeter times delta T. So we could calculate that, right? So that's negative, specific heat the heat capacity, 5.73 kilojoules per degree Celsius. And the change in temperature is 12.26 degrees Celsius. So negative 70.2498. So 3 sig figs, and what happens with the units? Degrees Celsius cancel out, and so the unit here is kilojoules. The calorimeter absorbed 70.2498 kilojoules, and the reaction lost that. Is this our final answer, though? No. It asked for the change in energy for the reaction in kilojoules per mole. This is the amount that was given off by 1.550 grams, right? Could we figure out how many moles that is? Sure we could. So we're going to convert this to moles. We want grams on the bottom, moles on the top. So we have to calculate a molar mass. 12.01 times 6 plus 1.008 times 14, 86.172. So 1.550 divided by 86.172. That's got 4 significant figures, 1798.72 moles. Delta E for this reaction is equal to Q for the reaction because this is at constant volume. So negative 70.2498 kilojoules. But I want to know how many kilojoules per mole. So I'm going to divide by the number of moles. So negative 70.2498 divided by 0.0179872 equals negative 3905.5. Sig figs, we should have 3. Units are kilojoules per mole. It's a big number. Is it okay? Yeah, it's okay. We can have big numbers. How do we round that, though?
3910 with no period.
Yeah. We can round that as minus 3910, no period, kilojoules per mole. Or you can put it in scientific notation. Scientific notation would be negative 3.91 times 10 to the third kilojoules per mole. Both of those are acceptable to me. You cannot round it to minus 391. It is not 391. It's 3,910. There's a big difference. Any questions?